Okay, sup guys. Today we're gonna continue and possibly finish our tree implementation, our binary tree. And we are going to focus on optimization today. And like the title says, we're gonna achieve this by creating our own hash table implementation. And I'm gonna tell you what a hash table is, but first we're gonna create a linear search method for our tree, so we have something to compare to, and we have something in case our hash table implementation doesn't find the right answer. So let's go into our code and create a lookup function. So basically we will have a key, a string, and we will turn that into another string. So our example tree looks like this at the moment. We are able to print this with our pretty printer from last time. If you haven't seen that episode, check out the link in the description. I will also link to the very first episode when we created our tree. So basically we have different folders, and inside of the folders we can have a key with a value, and that lookup function is what we are going to write now. So let's put it, doesn't matter actually, let's put it right here. And what are we going to return? Well, we are going to return a leaf, because that is what we are looking for, right? We have nodes connecting the stuff together, and we have leaves which contains one value. So we'll return a leaf, and we'll call this lookup with a suffix of linear, because this is the slow linear version. And all we need to provide is a string, so it's an int8 pointer towards an array, and we will call this our key, like so. And before we get into this linear lookup method, I'm going to create an alias for that. So like we did here with our find last leaf function, we just have a find last, which translates into the linear version. And when we have another version, we can change easily into that. So this is going to be our lookup function, taking one argument, and it will resolve to lookup linear at the moment with the same key, like so. Let me just double check that it updates, because I have been having Sociopath running for quite a while now. Let's see, lookup. Yeah, looks fine. So how do we look up something in our tree? Well, as I mentioned, our tree looks like this. So I guess I was a little bit fast there. We do need one more thing, right? Not just the key, because we can have the same key, a key with the same name in different places. We also need to have the folder name, the node. So two things. Let's go into the code and begin by altering this. So lookup of x and y. We will look up linear xy. And what is x and y then? Well, we have the key already. Before that, we will also have a path, like so. And the path we can easily turn into a node. So if we go to our, let's see, I'm not sure what we named that function. Let's go through here. So we have find last linear. We create node. We don't actually have a find node function. Perhaps we should create one of those. Yeah, I think so. Let me just add this new function here. So it's a leaf which is lookup linear, and it takes an int 8 pointer and another int 8 pointer, like so. And let's also create this new function, and that will return a node. So what should we call this? Find node linear. And this will only take the path. And let's see, we need to create an alias for this as well. So let's define find node with an x, and we will, let's see if I can line this up. This will be find node linear with an x, like so. Okay, so let's begin by creating that function. And where were we? Here. So we want a node, and we will call this find node, and we'll take the path as an in value. And how do we find this linearly? We need to add that suffix as well. Okay, so we need a pointer, a node pointer. Let's call it P. And we'll see what else we will need. So we do a for loop. We set P equal to the node representation of the root, and we are going to traverse this as long as P is true, and then P will be equal to P west. Because all the nodes are connected on the western or leftmost side. So let's see, what do we need to do at each iteration? Maybe we can do something like this. We will create another pointer which we call ret, and we will set ret equal to the node of 0, like so, and we are going to do a string compare. So if our p path is equal to our path, what do? Well, two things. We set return equal to p, and we break. And then at the end we simply return ret, because if we failed then it will remain 0, and if it worked out we will have our pointer right there. So let's test this out on our tree. So let's see, what do we have here? We have users login. Let's create a new variable, node test, and after we have printed our tree, let's just do printf pointer of find node, and the int 8 representation of the string users. Let's take log out first, so it should return a 0, right? Because we don't have a folder like that. Oh, what happened here? Pointer targets in passing, argument 1, string compare differ in signedness. That's it. So p path and path differs in signedness. Let's see. So where were we? Create. No, not create. Find node. Path is an int 8 pointer. We need to send these as chars. That's why. Because both of these are actually int 8 pointers. Like so. Node test, unused variable, control reaches end of non-void function, 104. That's probably just because we didn't finish the lookup function, right? Yeah. I accidentally closed this one. I'm too used to doing WQ when saving. Alright, well, I want this to the left. Let's see if it compiles without warnings this time. So we make it clean, we clear, we make, and boom, it works. Maybe. Yes, we get nil. And if we supply this function with a real path that we actually do have, so instead of log out, we call this login, because we create that right here. So if it works, it will return us a pointer. And it returned us a pointer. Alright, so now we can find our nodes in the tree. Next step is finding our leaves through this lookup function. And when we do the lookup, the first step will be to find the right node. So n will be equal to find node with the path. And if n is 0, we return the leaf representation of 0. Otherwise, we continue. So now we have reached our node. The next step is iterating through the different leaves connecting to this node and finding the one where the key is right. So let's do like we did in the last function when we find a node, only we do it with a leaf instead. So let's call this L, and we create a ret variable as well. Okay, so we do a for loop, and we set the leaf. First we set ret to 0, and it needs to be the leaf representation of 0. And we set our L equal to our node's eastern side, because that's where all the leaves are connected. So we begin there, we iterate as long as L, and each turn we do L equal L east. We continue eastwards until we are done. Yes. Then we do a string compare again. And this time I remember to cast those values. And what do we check for? We look at the leaf's key. And is that equal to the char representation of the key with small letters? If anyone knows how to disable caps lock on a Mac, please tell me in the comments, please. Okay, so what are we doing when we find the key? Well, we set the return equal to L, and we break. And that's basically it. Now we only need to return this stuff, because the only thing we are doing with this function is finding the leaf. So lookup is not a good name for it, actually. Let's change this to find leaf. That's better. Then we can create a separate lookup function which will use this function and return string. So let's see, we have lookup and we want it to be find leaf. Find leaf. Find leaf. And find leaf linear, like so. Did I miss anything? I don't think so, right? And then we can write our lookup function as well, and that will return an int8 pointer, a string. So lookup linear, and in this instance as well we do need a path, and we need the key. And let's see, we create a leaf we set p equal to find leaf, the path, the key, and then we return, if p is true, we return p value. And if it's not, what do we return then? Let's return an int8 representation of 0. Alright? And we will add it here as well. So int8 lookup linear, perhaps we should in this case actually specify that we want to use the linear one. So lookup linear, and we need to have an int8 pointer and another int8 pointer. And like before, we need to have an alias. So define lookup x and y, two parameters, and we will translate that into lookup linear with x and y. Like so. And it works. Let's double check that, by the way. So we are sure that everything works. So how do we do this? Let's just let's do something like this. We create an int8 pointer towards a temporary string. Can remove this one. And then we set our test equal to the int8 casted version of some key. So let's see, what do we have? We have Lucy and John. Let's do Lucy. And so let's, no, this is not what I wanted, by the way. Let's do it like this instead. We set test equal to lookup. And what do we want to look up? We want to look up the int8 of users login and the int8 of Lucy. Like so. And if test, we print it out. So just like this, and else we just print no. That ought to do it, right? So we make, and we run. And we get the value, same as here. Cool. I want to see what happens if we misspell Lucy. Lucy turned into Luke. No, okay. And finally, I want to see also what happens if we get the name right, but the path wrong. Oh, it works exactly as intended. Perfect. So next step is we want to create a big tree, a really big tree, and we want to test it in there. So I need to find something on Google. And that is definitely not the right program. Let's see. There we go. There is a list of all the, maybe not all, but a lot of English words. And I need that list. So let's see. List of English words in TXT. And I don't really remember which one it is, but I think I will recognize the web page. 1,000 most, 10,000 English word list. This is the one, I think. Let's see. Word list without the extension. That doesn't seem very W-gettable, perhaps. It's quite big. Let's rename it to wordlist.txt. So how big is it? 1, 2, 3. No, not that big. A megabyte almost. Let's see. Check the head of the list. Seems okay. The tail, and there are some characters at the end there. I don't like these Windows style things either. So there's a Linux command called call, which removes that. So you can do like call and from this to this, and then I'll just copy over the old one, the new one with the old one, like so. Still looks right. And if we open it up, now it looks good. And how many lines is it? 69,000. This would be perfect for our tree. So my take is we will create one node, so one level. We can use the node we have, and then we connect all of these 69,000 keys to that node with some value. Doesn't really matter what value. We can have let's see, we can have the key as a key, and we have the value as the key twice. That'll do. So this is the next thing we will do. Did you learn anything useful today? And do you want to support this channel? Go to drbirch.com/support. You can also click the button Become a Member. Thank you for your support. Okay, so let's begin by creating our new example tree. So let's clean out this main function. We can remove practically everything in here. So we will have a let's see, a tree, which we will call our example tree, and example will be equal to example tree, like so. And I want to create a structure which looks like this. So we have the root, then we have a folder inside of the root which is called A. Inside of that we have a subfolder B, and then we have A, B, C, and so on through the whole alphabet. And that will be our folders or our nodes. Then I will parse this English dictionary, and I will fill the A folder with all the keys beginning with the letter A, same with B, same with C, etc. And then we will have a perfect tree for our calculations and tests. Alright, so let's create our function signature. This will be a tree example tree void. And how do we do this? Well, let's begin by defining the signature. So the tree is called example tree, and we need a character or an int8, keeping track of the A, B, C, etc. We do also need a node, like so, and we need the path. So let's make this a string, path 256. And we begin by zeroing out our path. And then we do a for loop where we set the node equal to the node version of the root, and we set C equal to A. And we're going to loop as long as C is less than or equal to Z. And at each iteration, what are we going to do? I think nothing, actually. Alright. So first we need to create the path. So in the beginning, the path will be equal to slash. And then we want to, let's see, I think I will do it like this, by the way. So let's do C++. Okay, so C contains our character. So we need some kind of int as well. let's do an int 32 of n, no, not n, x, and do we need to initialize that? Let's do it just for the sake of it. And let's calculate the size or the length of the current path. So x will be equal to the int32 of string length, and into that we will send our char casted path. So this will be equal to 1 from the start. So then we will basically do path plus x equal to c, because c is our character, and we need to append this slash as well. So slash. So let's do a little space here, and we will do x plus, no, not plus, x plus. So we set it to the slash, and then we increase it by 1. So the next time we can just set it to C, like this. And the rest is already 0 initialized, so this ought to work. Let's do some debugging as well. Let's just print out the path, so we know that we're doing this right. Okay, so we have our path. Now we just need to create our tree. So n will be equal to create node, and I don't really remember the arguments for this one. So let's search for create node. We need a parent and a path, okay? So let's see, we need to save the parent then in another pointer. So let's do p for parent. So before we create the new node, we set p equal to the old one. And then it's n equal to the, let's see, p and path. And from the beginning, yeah, that's no problem. Alright, so we create that node, and I think we are basically done. Right? So now we just need to return this tree. And since we always begin at the root, we can simply do return the tree of root. And this should possibly work. So inside of main we set example equal to example3, and then we print tree example. Does it have any additional arguments? Let's see. Print tree. Yeah, we need an FD as well. So let's see. Standard in, standard out. It's 1. And yeah, this should be good. And then we'll simply free our, no, we can't really do that. Maybe we should create a function that frees up this stuff, but not right now. Let's see if it compiles or if we did mess something up. Make. Let's see what we have. Oh, isn't this beautiful? This is art, but there's a double slash at the beginning. Other than that, it looks pretty okay, right? I don't remember though, do we have to have a ending slash when we create the node? I don't think so. Well, that will be, we will see that if that is the case. Let's go to this again and remove this printf thing. So why does it give us a double slash? Yeah, because we add this here. So perhaps we should simply begin with a let's just remove this and see what happens. Okay, this looks better. This looks kind of perfect actually. It's beautiful in a weird, nerdy kind of way. Okay, so now we have our nodes. Next step is our leaves. So where should we put all of that stuff? We might need it later on, so let's create a function for this as well. What should we call that? We are going through a list of strings, and depending, well, this is another example function, isn't it? So let's do let's do an int 32 of example leaves, and let's do the signature right away. So tree, no, not tree, int 32 example leaves void, and let's highlight these examples somehow. So we easily find them when we want to clean up, if we want to clean up. Okay, so what do we need in here? We need an FD so we can open the file. We need a let's continue on with int 8. We need a buffer. Let's do 256. We also need a leaf L. We probably need a node as well. And we need a character, like so. And how do we move these on a Mac? No, not that. Where did we go? Well, let's do it the old-fashioned way. I want to have the same types of variables at the same place, basically. This'll do. Alright, so how do we create a leaf? We have a create leaf function, right? Create leaf. Let's do 2dd, paste, and we go to our main and above. Let's paste it here, turn it into 8 comments, and give us a little bit of space to work with. Okay, so we need a parent, a key, a value, and a count. The count being the number of characters in this. Alright. So I'm thinking we don't really need the, well, yes we do. We need to calculate the path somehow. Do we have to make it like a folder structure? Actually, yeah, let's do that, by the way, because that is how it will work in the end. So it's best not to change that. Okay, so then we need a little helper function creating a path. Alright, so let's call this int 8 example path, and we take in a character. And let's create our little signature as well. And this was an int 8 pointer example path. And it takes in a regular int 8. And what do we need here? We need an int 8 buff 256, and let's do basically like we did before. So we zero out the buff and we need a, let's rename this by the way. Yeah, okay. So we can create an int 8c and we do for loop where we set c equal to a. We loop as long as c is less than or equal to path and C++ again. And what do we do at each iteration? We still need to use an int32 counter for the length. So x is equal to the int32 of string length, and we give it the buff like so. Then we go to the buff plus C++ and set that equal to, no, not C++, X++. Let's see, buff plus 1, yeah, I think this is right. We set this equal to a slash. We copy this line, paste it twice, remove the plus, and set this equal to C, like so. And then we need to return the buff. And I do not want to malloc this because we'll be calling it a lot. So let's do this statically instead. Okay, I feel like I forgot something, but let's try it out. Example path int 8. No, it should not be. See, let's try it just by doing let's do printf s, and we want to do example path of the letter J and return. Let's see if it compiles. Nope. Warning, unused variable. Oh, never mind that. We are not done with this function. Okay, so let's see what it says. A, B, C, D, E. Okay, so it looks fine. I'm in a roll today. Not a lot of troubleshooting. only working stuff. It happens sometimes. Okay, so now we can produce this stuff. Now we just need a variable to store that into. So let's do int8 and path. And we will open up the file. So let's do the regular open. Example file, and we want to open it as read only. I think this is enough. And let's do assert fd, and what else? Yeah, we need to define that. So where do we have our constants? Do we have any? Yeah, we do. So we define our example file as wordlist.txt. And then we can have a while loop perhaps. So, and we need some kind of integer. Let's do int 32. What characters do we have left? X. So we set x equal to read fd buff 255. Before that we will zero out the buff. Like so. And let's see what the return value of open is. Of read. Man to read. On success, the number of bytes. Let's see. Well, let's continue on as long as it's positive. And we need for the open a couple of includes perhaps. I don't think we have this one since before. So let's add this one here. Alright, so we will loop as long as this x, let's do another set of parentheses, is greater than 0. And what will we do when we have read some data? I wonder if we get, we do get the new line. So let's begin by getting rid of that. So let's see. Buff, no, I need to check this. So if we have A, B, C, D and a new line, then we have indices 0, 1, 2, 3, 4, and the string length in this case is 5. So what we need is buff plus x minus 1, and we set it to 0. So now buff should contain the correct word in question, and then we'll need to calculate the path. So the path will be equal to example path, and we send the first character of the buff. That's the only argument, right? Yes. So then we get a string back with the path to the node. That's one step. The next step is to find that node linearly. So n will be equal to find node, and what are the arguments for that? Find node. It's only the path, okay? So n equal to find node path, and if we don't have an n, then we simply continue. But before that, we will do one other thing. I want to zero out the buff again. Like so. And if we have an n, then we can create our leaf. So let's copy this down. So L is equal to create leaf, and let's see, the parent will be the n, right? And the key is the buffer, but we also wanted to have the buffer twice as the value. So let's create a helper for that. Int 8 duplicate, and we take in a string, int 8 buff 256, we zero out the buff, we copy the let's see, into buff, into the char representation of buff, we copy the char representation of string with a maximum of 255. Then we set n equal to the int 8 representation of string length of the char representation of buff. So we have the length of the string. Then we do our next copy. And we need to do one security check, by the way. Let's see. X equal to the let's not make this so small. Let's do both of these at 16 at least. So the int 16 of the string length. Okay then, let's continue with our tree. So let's see, where were we? We're creating our duplicate function. So we are calculating the string length of the, let's see, it's the, this should be string copy. Yes, it's the key. We are calculating the string length of the key, but we are also calculating, let's see, the x will contain the n times 2. And if x is more than 254, then we will simply return buff as is. And if it's not, then we are going to string copy to the char representation of buff plus n. So at the end past our current buff, and then we will copy, let's see, we need to do string dupe because it doesn't like when it copies from the same variable to the same variable, usually not anyway. So that's why we do a string dupe here instead. And the source is going to be buff. String dupe buff. And we also need to specify a length, and this will be 255. So then we have the duplicate of that specific string, and we can simply return buff. This should be right, I believe. We do, however, need to make this static because we cannot return. If we didn't make this static, it will be allocated on the local stack for this specific function, and that the memory is not really accessible from the rest of the application. But by making this variable static, we are moving this variable to the BSS section, the uninitialized data section, and that is accessible everywhere. So that's one way of returning a kind of local variable. Alright, so this should be able to duplicate a string. Let's just double check that real quick, so we are not coding on something which will fail in that kind of way. So let's just print out s, and let s be the char representation of, what did we name it? Duplicate? No. Yes. Duplicate. And this requires an int 8 and then some string. Hello. So if we have coded this correctly, it should print out hello, hello on the screen, right? Let's do return 0 here. And I'm not sure if we have a half function somewhere which might get us into trouble, but we'll see, right? Yeah. Okay. What does it say? While warning, while clause does not guard ... this statement, but the latter is misleadingly indented. Well, error, continue statement not within a loop. Okay, I must have put a semicolon badly somewhere. And this should most definitely not be there either. This is inside of the function, okay. So where does it end? Or where does it begin? This while loop looks a little bit lonely, doesn't it? So let's see. Then we have this right here. And we need to return something temporarily, right? This is an int 32. So let's return the int 32 representation of a 0. Then we end this function. Okay, let's see what it says this time. Okay, a little bit better. Error, too few arguments to create leaf. Well, we are not done with this function quite yet. Yeah, this is where we are. Okay, let's just remove this for now. Two unused variables. Don't care about those. So let's run this. Hello, hello. Okay, perfect. It works exactly as intended. So let's, well, we can wait a little bit there. So where are we? We want to create a leaf. Let's see. Yeah. And we have given it a parent, and we have given it the key. The next one is to provide for a value. And I think we will rename this duplicate function, by the way, because I don't want this in the final implementation. So let's add this example prefix to it. And did we create a signature? I don't think we did. So this is an int 8 example. What did we call it? Example duplicate. And it takes an int 8 pointer, like so. So when we call this function, we are going to use our example, duplicate, and give it a buff. And what else do we need? The next one is, let's see, we're giving it the key and the value, and we need the count as well. Let's just do int 16. This will be a little bit too unoptimized. Let's at least create a pointer. So let's do, what should we call this? This is the value. So let's do val, and we'll just do val equals, and then we can refer to it right here. So we send the string length and the char representation of val. That ought to do it, right? And then we have created our leaf. Is there something else we need to worry about? I don't think so, right? So this will loop as long as we have anything in this file. Then we will want to close our FD, and we want to return the number of leaves, right? So let's do a variable for that. Or do we have one? X. How do we use X? We haven't really. Yeah, we did. No. Let's search for X. There. The X is the length, alright. So let's just name this Y then. And we zero this, we set Y equal to 0. And at each iteration, we just do Y++. And then we can return Y at the end here. And we don't need to cast it. Like so. Okay. And this name of the function is example leaves, and it takes no arguments. Right. So let's clean this up a little bit. Example equals example tree. We'll not yet print the tree though. We will, however, let's see, int32x, and let's print some kind of message. So printf populating tree ... and let's flush the buffer so it prints it instantly. Then we set x equal to example, what was it, leaves. Print out done. Something like that. And after the tree has been populated, we will print that tree to the screen. Okay, let's try this out. See if we missed anything. make. Okay, something is wrong. Operation on val may be undefined. Why is that? Is it because we're using a static variable? I think we should be okay. What else do we have? Variable x set but not used. And that is 265. I just want to check why we never used that. 265. Set but not used. Right, we're not printing it or anything like that. Okay, let's just do this. What length we go to make GCC happy. Warning, val may be uninitialized. Val will be uninitialized. Okay, that's the price of being lazy, I guess. Well. Let's move this then. And we'll put it somewhere right here. And instead of this whole thing, word. So we have buff. Let's see, we have n, we have buff, and we have val. This should be the right thing, right? Yeah. So let's make clean, space down a little bit and make. And this time it is only complaining about unused variables. I can live with that. Okay, let's see what will happen. Okay. Why does it print like that? Let's see it from the start. Populating tree, and then it prints some stuff. And A, we have A, and then did we add some weird printf somewhere to see if populating tree done? Slash standard out x equals example leaves printf done, and then we print tree. What happens if we don't print the tree? Then it looks quite alright. So we print example. I wonder if it's the printing function or the creation which messes up this stuff. Let's see the example leaves function. What do? We open the file, we zero this, we read, and we create an example path. We find the node. Wait a minute, let's see. And if we don't find the node, we continue. Okay. But if we do find it, we do this. Right. We should zero out the buffer, but I don't think that is the problem, actually. But let's do it anyway. Let's remove this message. I thought it would take longer than it actually did. And we don't want it to complain about this, so let's void the X. And let's see what happens this time. Perhaps we should pay some attention to the warnings as well. So what do we have? Variable L set but not used. 236. So 236. It's inside of the example leaves. But we're using it here, right? We are setting it here, but we are not referring to it. That's right. But we shouldn't need to. Let's just remove that then. Leave L. And what was the other warning? Unused variable C, 233. So we go to 233, and it's here. Okay, so the C, what did I think about the C? I probably thought of using that. Let's see. In order to check what path to put it on. But instead I referred to the first character of the buff. So let's remove C. Okay, let's see if it looks better this time. Let's make clean, clear, we make, and we run this thing. Okay, it does print a couple of these nodes, but it looks so weird. First we have the root, then we have /a, that's okay. Then we have /a, that's probably the first word. But then it all gets messed up. Why does it jump all the way to W? And what about the stuff in between here? Maybe we need some debug messages when we populate the tree. But before that, let's try doing a lookup on something. Let's see if we check the head of the file. Let's see if this Aardwolf is in the tree. So how do we do that? We call the function lookup, and what are the arguments? It's the path and the path should be the int8 representation of /a/ this, right? Or we need to separate those. So let's just do /a, and then this on int8 and that. I think it's like that. Let's double check the documentation, i.e. the H file. So we have this lookup linear, it takes an int8 and an int8. That's right. And I think this should be it. I'm not sure if we should have a trailing slash as well. Well, we'll see. Let's just do something like int8 p and p equal to this if p printf p else printf no. Okay, let's see how this goes. Example set, but okay, that's no problem. So let's run this whole thing. No, it does not find that one. Okay, we're getting closer. Let's test this out as well. No. Okay, so the problem is when it inserts itself into that tree. Let's remove this for now. This is a neat trick, by the way. We can use the preprocessor to do an if statement, and then we just end if. So this piece of code is not even in the compilation process. Alright, so how do we debug this the best way? I think before we create the leaf, we just print out the different variables. So we have something which equals something like so, and let's do something like this. And what do we have? First we have a node. And how do we represent that node? We can, let's see, node equals to, let's do not a pointer, but we go into the M and show its path. The next one is buff, that's easy. So buff equal to %s and buff. Then we have val, same there, val equals to %s and val, and finally we have the length. So we do len equals to %d, and we will simply just copy this whole thing. Put it right here. Okay, so this gives us a little bit of debugging information, and not so little actually. Alright, let's see what we have. And let's run tree and pipe it to more. So node equals /a, that's probably right. Buff equals to an a, and then all of this. Is that so? Okay, now I see. Oh, stupid me. The open and the read function doesn't behave as the fgetS function and the fopen functions. It does not read one line at a time, it reads a lot at a time. So we need to parse that on the basis of new lines. Right. Maybe we should just make our lives easier and use the library functions. It's only an example function, which will not be included in the final implementation. So let's do that. So where is it? Example path, example duplicate, this one, example leaves. So let's comment out this one. Thought I had a key for that, but no. And let's do a file pointer as fd instead. And we comment out this one, and we do fd equal to fopen example file, and we do the read flag. We assert fd, that's okay. We clear the buff, and instead of this one, we will do, let's see, we will use fgetS to get the buff 255 from the fd. But what does fgetS return? Let's check it out. Return value of fgetS returns s on success. That's a string, right? Where is it here? S. Right, it returns the buffer. And I need the size. Okay, so one additional step then. So let's just transform this. So while fgetS true. We do all of this. Temporarily remove this one. There. Okay, so we need to calculate x ourselves. X equal to the, how big is it? In 32, I think? No, it can't be. 8 maybe. No, it's 32. So the int 32 representation of string length, and we don't need to do this. Just put buff right here, because buff is already a, no, it's an int 8, okay. So then we need to cast this as well into char. And also when we call fgetS, we would need to do this as a char, and the rest is okay. And then at the end we will fclose, fd. I think I got it right. Let's see. No more errors, that's good. Let's do 3 and pipe it to more. Okay, this looks a bit more than I was hoping. So the node is this, buff is this, value is this, length is this. Okay, sounds right. Same here, same here, same here. Okay, this seems to do exactly that we wanted it to do. So let's remove this stuff. If 0. I don't want to delete it entirely because we might still need it. And then we go to our main, and we put all of this back. Let's run it like this, by the way, so we see if the lookup works. Make, we run 3, and we get nothing. We get nothing. So what do we have? Oh, okay, that's right. Let's put this back, because this is what we want, right? So make, and run it, and it's a little bit slower now, you see, when we're doing it correctly. Okay, it says no, but I think I know why. That's probably because we have this trailing slash right here. So if we remove that, we should get the value of that variable. Yes, we do. That is correct. So it's the word Wolf twice. Exactly what we want. Okay, so now we can finally print out the, and I closed the wrong file. As usual, those vim commands. So let's get this down and this to the right, and now we will just delete this stuff, and we will print our beautiful tree, hopefully. So we do make clean, jump down a little bit, run make, sounds good, and we run tree. There we go, that's how it should look. Isn't it beautiful? Let's pipe it to more so you see more of it. Okay, so here we have all the different English words, and they are in the correct folder as well. What if we go down to the B? A long row down. Oh, here it is. So here we have the B words, and then we get down to the C words, and everything looks exactly as we would like it to. Okay, that's cool. So that's enough for this episode. I think we will need one additional episode where we optimize this and go from the linear to better implementation. But this far, everything works. So if you like this episode, please like and subscribe so you don't miss the next one. And thanks for watching, and thanks for today.